Hello and welcome to the specific heat review. It's going to be a quick review on specific heat and some calorimetry as well, and that's actually where we're going to start with calorimetry. So calorimetry is usually how we are going to look at heat flow. So calorimetry is the measure of heat flow. A calorimeter itself is a device capable of measuring heat flow. So something like this coffee cup calorimeter over to the right. There's also bomb calorimetry, which we're not going to look at in this video, but we're going to look at coffee cup calorimetry and how we can find specific heat using that coffee cup calorimetry. We're looking at our heat flow at a constant pressure. So our delta H is going to be equal to our heat at constant pressure, so Q subscript P, and our calorimetry measures that delta H for a reaction. Remember, or think, as you add heat to a substance, that substance will in fact get hotter. As you add heat, increase in temperature, more heat, more increase in temperature. But we have to think about how much it's going to increase. So any substance, the more heat you add, the more it's going to increase its temperature. But the amount of heat you add is not the only factor. It's also dependent upon the heat capacity of the substance itself. So if we have a significant heat capacity of a substance, then it's going to require more heat to increase the temperature of that substance. And it's also going to hold on to more heat as you cool it down. So greater heat capacity for a substance, the more heat that's required to heat that substance up, and the more heat that's released as it is cooled down. Our heat capacity is given by the symbol C, or letter C, and it is the amount of heat in joules required to raise a substance's heat by 1 Kelvin or 1 degree Celsius. They are interchangeable because the change in those temperatures are going to be the same in magnitude. If we have a pure substance, we look at either the molar heat capacity or specific heat, where our molar heat capacity is equal to joules over moles times by Kelvin or degrees Celsius. And then our specific heat, which is what we almost always look at, is going to be joules over grams times by degrees Celsius. You can convert between the two by just multiplying. To go from molar heat capacity to specific heat, you're going to multiply by your molar mass. To go from specific heat to molar heat capacity, you're going to divide by your molar mass. The equation to determine your specific heat is joules or your heat transfer divided by the mass of your substance times by your temperature change. And then you could also figure out your molar heat capacity by taking heat transfer divided by the moles of substance times by the temperature change. Generally, again, we look at specific heat, and we can look at this equation as well, just rearranging. We can take the heat transferred is equal to the mass of that substance times by the specific heat of that substance times by the delta T of that substance. So if you have all of this information, you could also solve for the heat change that you should, or the heat that is absorbed or released to see a specific temperature change within a substance. Here's a table of some specific heats you'll see. Something like water, very, very high specific heat because of its intermolecular forces, hydrogen bonding. Hydrogen bonding is going to cause it to not want to move away from the substances which is required as you heat that substance. A metal, such as mercury down here, has a very, very low specific heat. Any metal, as we should know, is something that can heat very quickly and easily, cool down very quickly and easily. That's why we use metals in order to cook with. And then, covalent compounds, nonpolar covalent compounds, kind of lower specific heats because they're easier to heat up. Let's try an example. So if we have 487.5 joules of energy, we want to heat, or it is required to heat 25 grams of copper from 25 degrees Celsius to 75 degrees Celsius. With this information, we want to determine what our specific heat of our copper is. We use the equation Q is equal to mass times by specific heat times by delta T. Thing to keep in mind with this equation, you're going to use the same thing all the way across. So you'll use your Q of your metal is equal to the mass of your metal times the specific heat of your metal times the delta T of your metal. We can rearrange this to the specific heat of our metal is equal to the Q divided by the mass times by delta T. So our specific heat equation, and that'll be the easiest way to actually solve for this. Here is our Q, our mass, and our delta T. Remembering that delta T is equal to T final minus T initial. Okay, so we have specific heat of our metal is equal to 487.5 joules divided by our mass, 25 grams, times by our delta T, 75 degrees Celsius minus 25 degrees Celsius, giving us 50 degrees Celsius. Solve for our specific heat, we get 0.39 joules over grams times by degrees Celsius, a reasonable value for a metal. Okay. One of the things you guys did in 1211 is looking at constant pressure calorimetry. So when we have a reaction done in a calorimeter that keeps a constant pressure. In order for it to keep a constant pressure, we have to be able to allow the removal or addition of air. So we can't bottle up a system, we can't have an airtight system, so it has to be open to the environment or have a flexible or non-airtight lid that allows air in and out. We call this constant pressure calorimetry, and we most commonly use a coffee cup calorimeter. So we're going to take and put our reaction in an aqueous medium, and then we're going to look at that water temperature change to determine how much heat was gained or lost by the water. And we can use Q reaction, so the reaction that's within the water is equal to Q solution. Q solution is our Q of our water, or water plus solute, right? Solution is solute plus solvent, where water is our solvent. So we're going to look at the heat absorbed or released by our solution or our water, and then that will determine what our reaction has gained or lost. So if we want to determine that, the Q solution, we're going to take the Q solution is equal to the mass of our water times by the specific heat of water and our delta T of our water. So let's try an example. So we've got metal. We throw this metal that's 100 degrees Celsius into water. So this metal is equal to our reaction. And then our water is our solution. This is not an actual solution, but same idea here. So our water is going to be at 23.7 degrees Celsius initially, and then it's going to heat up to 27.8 degrees Celsius after that metal is added. So we're going to take our Q of our water equal to our mass of our water times by the specific heat of our water times by our delta T of our water. So we can determine what that heat, the heat that was absorbed or released by the water, and then that will be the negative of what is released or absorbed by the metal. So our Q of our water is equal to our mass of our water. We're given volume of water, 100 milliliters. Density of water is 1 gram per milliliter, so this would be equal to 100 grams. Our specific heat, 4.184 joules times by grams degrees Celsius, and delta T is going to be 27.8, 27.8 minus 23.7. So if we solve for this, we get a Q for water equal to 1715.4 joules. Positive, that means that it's absorbed heat. Our Q of our reaction, or our metal, is equal to the negative Q of our water. So our Q of our metal is equal to negative 1715.4 joules, which makes sense as it's cooling, so it's releasing energy. So we'll put that into our equation. Our mass of our metal is 59.047 grams. We're solving for our specific heat of our metal. And our temperature change, our final, is lower than our initial because we have released energy. It is cooling down. So 27.8 degrees Celsius minus 100.0 degrees Celsius. Solve for this, we get a specific heat equal to 0.402 joules over grams times by degrees Celsius. Again, this is under 1, so this is a reasonable specific heat for our metal. Hope this has helped you guys review for your specific heat. If you have any more questions, please let me know.